We have learned three types of grammar that we can use for top-down parsing. The first one is LL1 grammar, grammar that can has this form, where alpha is a combination of both non-terminal and terminals. The second type of grammar that we have discussed is translation grammar. It is LL1 grammar that has been extended to produce output. We have also discussed attributed grammar. So this is grammar that is capable of passing attributes from one rule to another in the same grammar. Now we will combine what we have learned and apply it to a new type of grammar called attributed translation grammar. And just like its name implies, this is a grammar that is capable of producing output and also passing attributes from one rule to another. The grammar that we will discuss in this lesson is capable of parsing input involving arithmetic operation with addition and multiplication. And the output of this grammar will be a stream of atoms. We have discussed streams of atoms previously in topic 2, and we have also did translation exercise on it. So just to recap, if you have an input in Java like this, A plus B, the output in the stream of atoms form would be add A, B, and store into T1. In this grammar that we will discuss, the operators will be presented as action symbols. So we will have add action and also mul action. Meanwhile, the operands will be the attributes of our action symbols. So we will have a left operand, right operand, and results of the operation. So for example, if you have this string A plus B times C plus D, the output must be something like this. Multiply B, C, and store into T1. Add A with T1 and store into T2. And add T2 with D and store into T3. So this will come from the grammar, and we do not need to think what would be the order of the operations, and we will get this output from applying the input into our grammar. This is grammar 21 that we are talking about. This is a grammar, an attributed translation grammar that can accept arithmetic expressions for addition and multiplication. This attributed translation grammar has action symbols. So this is action symbols add for addition operation, and what this basically will do is it will put out an add atom with the operands P and R, and the result will be stored in S attribute. And then we will also have an attribute computation rules. So this particular method here will be called when we are finding the attributes for S. This allot method is a method to allocate space for temporary result. Therefore, if we call allot for the first time, it will return T1. If we call it for the second time, it will return T2. Third time, T3, and so on. All non-terminals attributes in this grammar are synthesized except for the first attribute of elist and tlist, which will be inherited. And then, when symbols share an attribute, it means those attributes share the same value. So for example, if you see here, rule 7 and rule 8, factor here has the attribute of P and ident here has the attribute of P. They would share the same values. Same goes for rule 7. this P will share the same value. Now, based on our understanding of atoms, if we have this expression, the input we should get is at A, B, T1. Now, let's see if we can produce the same output by applying grammar 21. So, I'm going to start with the starting non-terminal, and our starting non-terminal is expression. So, expression can be derived to term Ellis. So when we start drawing the tree, we are ignoring the attributes first. Okay, we are currently trying to write A. Our current input is A. So for term, there is only one rule derived for term, rule number 4. Term can be derived to factor T-list. And for factor, there are two rules derived from factor, rule 7 and rule 8. I will be choosing rule 8 because I want to write an identifier. A is an identifier. Therefore, factor can be derived to identifier, and I will write the attribute as A. So this is done. Next, we move on and we want to write plus, and we are writing it under T-list. There are two rules derived from T-list, rule 5 and rule 6. Rule 5 is for multiplication. Therefore, we will be applying rule 6, which is to epsilon. When it is derived to epsilon, it means we still haven't write plus yet. So we move up to E-list. For E-list, there are two rules derived from E-list, rule 2 and number 3, rule 2 and rule 3. And the rule that has plus in its rule is rule number 2. So I am applying rule 2 here. Plus term add action and E-list. Okay, so we are done with plus. Next, the final input is B, and I will write it under term. Again, term only has one rule, rule number 4, factor T-list. Okay, factor derived to ident. Since B is an identifier, I'm going to write the attribute of B. So we are done. However, you will notice that we still have some non-terminals hanging, and we cannot leave an attributed derivation tree with non-terminals at the end. Therefore, T-list here is assigned to epsilon, and E-list here derived to epsilon. Okay, the skeleton of the tree is now complete. Now we need to parse the values. So I'm going to start from left to right and from bottom to top. So here is rule number 8. We already know the value for P. We do not know the value for factor, the attribute for factor. But since they share the same attribute P, because this is A, ident's attribute is A, factor attribute should also be A. Okay, now moving up, this rule over here is an implementation of rule number 4, this rule. So in this particular rule, we already know the value or the attribute for Q. And that attribute is A. We do not know yet the attribute of P. Because Q here has the attribute of A, the Q here must also get the attribute of A. So I'm going to write A, but we do not know the value of P yet. So the value of P is still blank. To know the attribute of, the value of attribute P, we need to look at this rule, T-list to epsilon. So this t list to epsilon is actually an implementation of rule number 6. So for rule number 6, we already know the value for attribute P, which is A. We do not know yet the value for attribute Q. But if you look at the attribute computation rule, it says that Q should get the value of P. Therefore, since P is A, Q will also get the value of A. Now, moving back to this rule again, rule number 4, term can be derived to factor t list. And if you look at this particular section, t list has two attributes, Q and P. Now, if you look at our t list at the tree, the two attributes are A and also A, which means P now has the attribute of A. So we see P again as the attribute of term. Therefore, our term here will get the attribute of A. Now, moving up, we are looking at this rule. Expression can be derived to term and list. And this is an implementation of rule number 1. Now, let's look at what value of attributes that we already know. So, the value that we already know is Q. And Q has the value of A. We see Q again here as the first attribute of list. Therefore, the first attribute of list, so list has two attributes, Q and P. So the first attribute of list will be A, but we do not know the second attribute yet. To get the second attribute of list, we must synthesize it from the branches below. So moving on, let's look at this particular rule. Factor can be derived to ident, which is an implementation of rule 8 again. Because rule 8 has the same attributes P and P, and the attribute of P of ident is B. The attribute P for factor should also be B. Okay, moving up, let's look at this particular rule, which is term can be derived to factor t list. So this is an implementation of rule 4. So from this rule, we already know the attribute of Q. And we meet Q again as the first attribute of t list. Therefore, the value of t list over here, okay, t list has two attributes, Q and also P. So the first attribute will be B, because this is the same attribute as this. The second attribute is unknown, but since t list is derived to epsilon, and this is an implementation of rule 6, and we have looked at rule 6 previously, where it states that Q gets the value of P. Therefore, it is safe to assume that the second attribute is also B. Okay, moving up to term factor t list rule again. The attribute of, okay, let me move this first. Okay, the attributes here are Q and also P. We already know both values, both are B. And we also see P again as the attribute of term. Therefore, term here gets the value of B. Okay. Now, we need to fill up the attributes of add atom. So this add atom has 3 attributes. So if you look here, we are looking at rule number 2. Add atoms has 3 attributes: P, R, and also S. So I'm going to write underneath it because we do not have space. P, R, S. In the same branch of this rule, ELIST can be derived to plus term add and ELIST. We already know the attributes of, first of all, P. And that attribute is this. Okay, so I'm going to write the attribute of P as A. And then we also know the attribute of R. And that attribute is this, which is B. So I'm going to write the second attribute. R has the value of B. And then we need to figure out the value for attribute S. Attribute S, we look at the attribute computation rule and it says call method alloc. If you still remember, alloc is a method to call for temporary space. So this is the first time we are calling this method, therefore we get the value of T1. Okay, so we are done with this, and then we move to the next symbol, which is ELIST. ELIST has 2 attributes, S and Q. S, we have established S as T1. So let me redraw this tree because we do not have space. So this is ELIST to epsilon, and ELIST has 2 attributes, S and also Q. So S, we have established S as T1, and then Q, because ELIST is derived to epsilon, it is safe to put the attribute of Q as T1. Okay, and then moving up again, going back to rule number 2 here. Okay, so let me rub all this first off so that we can see clearly. So we are looking at rule number 2. Okay, so we already know the values for P, R, S, and also Q. Q currently has the value of T1. We also see Q as the second attribute of ELIST. Therefore, this Q also gets the value of T1. And finally, we can move up one level to this branch and this rule. So this rule is actually rule number 1. So let's look at rule number 1 at grammar 21. So we already know the value of Q, which is A. So this is Q. We also know now the value of P, which is T1, and we see P is also the attribute for expression. Therefore, the attribute here next to expression will be T1. Okay, so our tree is now complete. To get the output, what we will do is to list out the action symbols only, or the atoms only, and we read it from left to right, bottom to top. But since our tree only has 1 atom, it's going to be easy, and the atom is add, and the attributes of add is this. So our output is add and the attributes are A, B, T1, and this is exactly the output that we have stated at the beginning of this slide. So this is how you get the output from an attributed translation grammar. Next, we're going to look at an attributed translation grammar that can do many operations. So the arithmetic operations are addition with add atom, multiplication with MUL atom, subtraction, and this is the atom, and division. This is the atom. It can also handle Boolean expression. It uses test atom, but it will branch when false. And it also employs comparison could. We will take a look at comparison could table later. This grammar can also do an assignment operation where you pass values into identifiers, and it uses move atom. So the name of this grammar is called decaf grammar, and this is a play of word because the Java programming language is also the name of a type of coffee. And this new attributed translation grammar that we will discuss, the decaf grammar, has lots of capability of Java, but it is not as powerful. It can only translate until atoms. That is why it is named decaf. There is no caffeine, so there is no kick.